Okay, welcome everybody. Finally got everything set up properly, which is good. And we're going to go ahead and get right into Chapter 2. Okay, I've got the chat pulled up, so if you need to ask anything, go ahead and put it in there. And I'm going to just kind of briefly review what we talked about last time. We talked about the different components that we're going to use. We talked about resistors and capacitors, and we talked about inductors. Not in depth, but at least we know those terms now, right? We also talked about semiconductors and LEDs and regular diodes, and also introduced the concept of a transformer. So those are kind of the components that we'll be working with throughout the semester, okay? Again, we will not be using a physical oscilloscope and a function generator, but here on the left, we're going to be using a DMM, right? And in lieu of a nice digital display power supply, we're going to be using a 9-volt battery, but it's still going to accomplish the same thing. So we also talked about the difference between conductors versus insulators versus semiconductors. And again, I will go ahead and change this. Insulators really 6 to 8. Semiconductors, 4 or 5, but it could be 3 depending on the compound. Okay, so for the most part, 1 to 3 valence electrons, if they're on the left side of that periodic table, they're going to be good conductors. Okay, they allow free electrons to move because there's a lot of space in that valence shell. Remember, the valence shell is the outer orbital shell of an atom. And so if you only have 1 to 3 there, you have anywhere from 5 to 7 spots where free electrons can move. So that's why we use a lot of metals: gold, silver, copper, aluminum, that kind of thing. If that outer valence shell is essentially full or close to full, there's not very much room for free electrons to move. And so we actually wrap conductors with an insulator so that we can hold them. Okay? So glass, ceramic, rubber, wood, plastic, noble gases, that kind of thing. Semiconductors are right in the middle, and for the most part, we just work with silicon. Nobody really uses germanium anymore unless you're an audiophile and you want sort of that warmer sound that a germanium transistor might give, let's say. But, outside of that world, everything is silicon because silicon is stable, and I talked about how if you have your phone, you want it to work if it's negative degrees outside, and you also want it to work if you take it in the sauna and it's 180 degrees. So now, if you do take it into the sauna and use it, let's see. Oh, Tommy said I was sitting in the Zoom meeting this whole time. Okay. So anyway, unless you are in that world, you want something that's stable across all temperatures. Okay, and so that's why we use the silicon transistors and diodes usually. Okay, so some of the safety rules that we talked about, I still have never adjusted this slide here, but work with a buddy. Don't wear jewelry. Don't wear any big chains or big rings. I even said that I take off my wedding ring when I do some of this stuff. I don't do it always, but just to get into the habit of not having any metal on. Just like if you were going to work on a lathe, you wouldn't wear a tie, right? Because of safety issues. So you wouldn't wear anything metal. You wouldn't have anything wet around where you're trying to use electricity because, remember, water will actually reduce, it'll lower the resistance. And anytime you lower the resistance, you're going to increase the current, which is bad news for human beings. Okay? So there's more safety rules. And we talked about some of those in the last lecture. Okay, we also reviewed Coulomb's force equation, and have 2 charges. What's the distance between them? And then you can measure the force, or you can calculate the force. Okay. So today we're going to talk more about current flow. Okay, I think we've got the concept of the atom. And not how electrons move, but the fact that electrons can move from atom to atom if that outer shell has some space available, right? So if it's a conductor. So we understand that, electricity is going to move from atom to atom along some wire. It's going to go through some components. There's going to be voltage drops across each component. There's going to be a current through each component, and I try to be very careful about how I say each one of those, that we have voltage that drops across a component, and we also have current that goes through a component, okay? So I sort of like the analogy here, pipe filled with tennis balls, however big the diameter of the pipe is, that's how many can fit down the line. And then how quickly it moves from one end of the pipe to the other end, that is a rate, right? We talked about how if I move from point A to point B, that's my displacement. I measure that in length. And then if I want to know how quickly I got from point A to point B, I take the derivative and I end up finding the velocity, right? How many meters per second if you take the derivative with respect to time. So, we're not doing any calculus in here, but it's the same thing. So you have voltage, you have a voltage potential in a battery, and then if you have a complete circuit, you're going to generate current. Okay, you're going to draw current from that source. In other words, the electrons are going to move from one point in the circuit to another point in the circuit. Okay. So here's how we define the I, and we do not use C for current because we use C for capacitance. So the guy who invented, or not invented, but actually discovered, I always say that backwards. It's not invented. These folks are discovering things, right? So the person who discovered current, the way that electrons move, his last name started with an I. And so it's defined as charge over time. So like it says here, 1 amp equals 1 coulomb of charge. Remember, 1 coulomb of charge is nothing more than 6.25 times 10 to the 18th electrons. Somebody gathered up that many electrons and said, that's 1 coulomb. And so 1 coulomb flowing past one point in a circuit in 1 second is 1 amp. Okay? So again, Q measured in coulombs, capital C, and then time. I don't like, this is a picture, otherwise I would change it. But I really like using the lowercase t for time. When I see the capital T, that always reminds me of, well, for one thing, PV equals nRT, if you're familiar with any physics, right? So PV equals nRT, where T is the temperature. And also, T is also used in this class for period. So what's the period of a sine wave, right? How long does it take to complete one cycle? That's the definition of a period. So really this should be Q over lowercase t, okay? Now it's not that big a deal, but I've never liked that it's the capital T here, okay? So anyway, current is the definition of a current is that it's 1 coulomb of charge moving through one point in a circuit over 1 second. That's 1 amp, or the full name is ampere, but we always just use amp for short, okay? And so current is measured in amps, charge is measured in coulombs, and obviously seconds is just lowercase s if we use our SI units. So again, resistance, the entire reason why we use resistance in a circuit is that it opposes the flow of that charge. And I said before, you might think to yourself, well, why would you want to reduce the amount of charge? Well, certain components and certain loads operate off a certain current operating range, okay? So they might have a certain voltage that they need to operate, but they may also have a certain operating range for current. So I use the example of the LED, the light emitting diode, right? That has an operating range of 10 to 20 milliamps, or 10 to 20 thousandths of an amp. In other words, 0.01 amps, right? Or anywhere from that to 0.02 amps, right? Now, we're going to get more into the engineering notation, and we are not going to, this bothers me even typing it out because I don't live in this world here. I live in the world of using our engineering notation and saying 10 milliamps and 20 milliamps. That's the operating range of a diode, okay? Now this is an example of, I'm just typing over this slide here, but I'm just saying that an LED has an operating range of 10 to 20 milliamps. So if you put in 100 milliamps, 5 times more than the top end of the range, then you're going to burn it up, right? You're going to blow it up. So we use resistance very, very particularly when we have these loads, and that way we make sure that we do not overcurrent them, right? We don't have too much current being blasted into whatever it is we're trying to operate, okay? Some components have a much higher operating range, and some components have a voltage and a current rating on them. So, or they have a voltage rating and a watt rating, right? So you can only put so much power through them. So resistance, just in general, if you just wanted to calculate it, you could take the voltage that you measure on a component, and then the current through that component. If you take V over I, that will give you the calculated resistance. If you want to look at a resistor, how it's defined, it's whatever the material is times the length over the cross-sectional area. And this material, this could be copper, this could be aluminum, this could be gold, this could be silver. And so that rho, this Greek letter rho, is going to be different for every type of resistance. And so this is just a piece of wire, right? So if you have a 14 gauge wire, so that would take care of the cross-sectional area, and it's 2 feet long, and it's made out of copper, you could calculate the resistance of that conductor, okay? So we measure resistance in ohms, and that is the Greek letter that you see here. And so a lot of times you'll see me write, like 2.2 kilo ohms, or I'll actually use the symbol for it, okay? So something like that, except no space. So 2.2 kilo ohms is how I would read that. In other words, 2200 ohms. And we'll get into the prefixes here in a little bit. But anyway, ohms is the unit for resistance, and we use the Greek letter omega to express that, okay? And again, 1 volt over 1 amp equals 1 ohm. Right? And it says 1 ohm is the amount of electrical resistance that limits the current to 1 amp when 1 volt of electromotive force is applied. That is the technical definition of it, okay? I usually don't talk like this when we actually start doing these calculations. So conductors, you don't want them to have a very high resistance. Now, in some cases, you can't get away from that, like transmission power lines, right? Those are pretty thick cables. If you've ever seen one up close, the overhead lines that line our streets, that deliver power to neighborhoods and residences and things like that, those are pretty big, thick cables. And so those actually do have quite a bit of resistance in them, but you need something that big if you're going to transmit potentially hundreds of thousands of volts on it, okay? So we don't work with anything that big. We're working down at the board level. So we're using I forget what gauge wire comes with your kit, but it's not very thick. It's like maybe 26 gauge or something like that. Pretty thin, right? So if you take a piece of wire from your kit that you're going to get, and you measure, like a 4-inch piece, it's going to be less than an ohm, like milliohms. So you don't really want conductors to add a lot of resistance in your circuit. If you want resistance, you want to actually put in resistors, and so you can control that better, right? So semiconductors, they can be like 20K, 32K, so 32,000 ohms, 20,000 ohms, somewhere in there. And it's not as important what that resistance is, because most of them, like if it's a silicon diode, the big thing you're worried about is, does it have at least 700 millivolts across it to operate? So, insulators, we do want them to have a huge resistance, right? Because we don't want them to easily pass current. So insulators should have a big R that's so big it's either in the milliohms, I'm sorry, mega ohms or the giga ohms, or even, you know, once you get above giga ohms, you're essentially at a what would you call it, an open circuit, right? Because there's just no current that's going to flow with that much resistance. Now your body has a high resistance, and it's in the mega ohms, and it says lamps have a relatively low resistance, right? Because you know, if you've ever taken a lamp apart, just a standard light that plugs into the wall, it's basically two wires that connect to one side of the light bulb fixture and another side of the light bulb fixture. But it's basically tied right into the wall. There's very little resistance there because the resistance comes from the lamp itself, the actual light bulb. So, you know, if it's a DC light, then it works a little bit differently. Like an LED, I've got, you know, my box lights that I have to make this a little bit brighter when I use my camera. My box lights are LEDs, right? And so it's got something inside that converts it to, you know, or it might just use AC power. I don't know. I haven't taken it apart, but you could easily power LEDs and have them stay on with DC power. Okay. So just to reiterate, the three fundamental quantities that we are going to be working with in here is voltage, current, and resistance. Okay. I'm not going to go through these. I'm going to show you this on the board, what their relationships are. Okay, so let's go ahead and talk about the basic circuit. And this is, boy, if I made you write all of your components like this, you'd have to take an art class too. But anyway, here is a battery, here is a switch, and here is an LED that's turning on. Now, if you do have any circuit experience, you know that you can never just hook up an LED to a battery, okay? Unless the battery has enough internal resistance to where it's going to limit the current, but that's very doubtful. So again, if you just hook this up to a battery, it's going to blow the LED, right? Now there are situations where that may not happen, but if you were to connect, let's take this 9-volt battery out of here and just put one of the power supplies from school there. If you were to hook up an LED across those terminals, you're going to blow it, because the only resistance in that closed circuit is whatever the wire is. And I just said that conductors are, you know, less than an ohm. So let's just say this is 9 volts. 9 volts, and let's give it the benefit of the doubt and call it 1 ohm. Okay, that's going to be 9 volts divided by 1 ohm, which is going to give us 9 whole amps. Well, this LED will not operate at 9 amps, and so it will blow. It will burn up. So I wish I could redraw this picture with a resistor, at least limiting the current to that LED. Okay, but anyway, here we have. You know, one of the other important things about this picture is you see that it's a closed circuit. If any part of this is open, it will not draw current. Okay, there will be no voltage drops, there will be no current, it won't operate. So you have to have a closed loop. That's very, very important, and it's going to be very important when you actually have to hook this stuff up to your breadboard and make the connections on your own. Okay. All right. So let me see here. Before I get into that discussion, I'm going to talk about, I'm going to flip over real quick to my camera. Have to be very ginger. I don't have this screwed down like I did in the garage. And I've got everything glued up. I just didn't get it done. I'll definitely have it before Monday, my little studio setup, so I'll be in there. But anyway, V equals I times R. We're not really getting into the discussion of Ohm's law just quite yet. However, I just want you to look at this equation here, right? So resistance times current equals voltage, okay? So if I have a constant voltage, let's say I have a 9-volt battery, right? So that voltage is not going to change. It's static. Okay? if I have a decrease in resistance, I'm going to have a corresponding increase in current. Okay? It has to happen. If this remains static and this one goes down, this one by default has to go up. Okay? This is called, what is it called? That's an inverse relationship. They are inversely proportional. Okay? That just means if one goes down, the other one does the opposite. Okay? So we could have the same thing. If you have the same voltage but you increase the resistance, that's going to automatically decrease the current. Okay? Now, let's say we have a variable power supply, but we have fixed resistors, just like you're going to get in your kit. Okay? So now this is constant, but this one can change. All right? So if I have an increase in voltage and my resistance doesn't change, that automatically means my current has to change proportionally. Okay? Those are called directly proportional. Okay? And the same thing happens if somehow we had a constant current, which there are current supplies that you can make, but there is no, like, you can't store current. It's like trying to store flux, which is why the flux capacitor in Back to the Future is so clever, because they're saying that you could actually store magnetic flux somehow. Same thing, you can't store current because current is a rate. You can't store speed, you can't store current, okay? But let's say that we had a constant current source, all right? You can see that if you were to increase the resistance with a constant current source, you are going to, by default, increase the amount of voltage, okay? Same thing. If you increase the voltage, okay, you're going to have a direct increase here as well. Just they're directly proportional is what I'm trying to show you here, okay? You're not going to be quizzed on that. It's just, you know, if we're working through this and, you know, you've got some circuit that you're building, and let's say this is a 100. These numbers don't matter, by the way. Let's say this was 100 ohms and this was 200 ohms, okay? And here you've got your source at 10 volts, okay? So this one stays the same. And if you make this one 300 instead, right, that goes up, the calculated current would by default go down. So what I'm trying to get at here is as you work through these calculations, it goes back to the point 4, you know, I talked about the problem solving method. What's the very last question you ask yourself? Does this answer make sense? So if I say, okay, here, calculate what the current is here. Now replace the 200 with a 300 and then calculate the new current. You should know that you should get a smaller current when you do your calculation, okay? So I'm just pointing out the relationship here between the three variables, okay? And that may be obvious to you, but I always like to just point out that current and resistance are inversely proportional, and voltage and current are directly proportional. Okay? All right. So, let's talk about engineering notation. All right? If we were scientists, let's say we were chemists, okay? All of my chemistry classes, I never used any prefixes to my knowledge, to my recollection, even through organic. But what we used is scientific notation, okay? Now, scientific notation is when a number is between 0 and 10, right? And then it's times 10 to the whatever, so some x. And it doesn't matter how big this number gets. It could be the negative 28th, it could be the 29th, it could be the 17th. The big thing is you always report it, that very first value, as a number between 0 and 10, but not including 10. So in other words, 9.45 kilonewtons. That is science, or I'm not kilonewtons, but Sorry, I just did engineering notation. I'm so used to it. 10 to the 45th newtons. Boy, that's a lot of force, right? The main thing is this number is reported in a value that's between 0 and 10, but not including 10, and then the exponent is whatever it is. And we don't really care what that number is. We let our calculators do the math, okay? Or it could be 10 to the negative 28, you know, maybe like 1.45 times 10 to the negative 28 moles of some substance, right? So that's the kind of stuff that you do in some of the other sciences. Okay, now if we're talking about measuring and trying to qualify the measurement of a circuit, and I say, hey, on that last problem, I got 0.00003 amps. Okay, now you're making me do math in my head because I have to count how many zeros were out in front. There was 1, 2, 3, 4, plus the 3 gives me 5. And so, you know, I know that that's 3 times 10 to the negative 5 amps, okay? But that's kind of a crummy way to qualify a measurement because then I have to, you know, in my head think about what that actually means, right? That's actually 30 millionths of an amp, okay? So if I'm going to think about that anyway, like 30 millionths, then why don't we just write it like 30 millionths? So instead of writing this, I would write 30 microamps, okay? So what the micro does is it tells me in lieu of 10 to the negative 6, I use what's actually the Greek letter mu. I bet I can find it real quick. It's the U with the little tail out in front. If I can get to my Greek letters. Greek. Well, now I don't see it. Where's my lowercase? Oh, here it is right there. Yeah. So it's the mu character. So this would be, you know, 10 to the negative 6 is the same thing as putting in the micro. So instead of having to write this, I just use this little prefix, and then I can say, oh, okay, I'm talking about 30 millionths of an amp. Or if I use milli, that's 10 to the negative third, okay? 30 milliamps tells me that's 30 thousandths of an amp, okay, with the M out in front here. So what we're doing is we're utilizing these powers of 10 to the 3 and arranging them in such a way that you know, we can quickly qualify a measurement just by you telling me what you got, right? So here is the breakdown, and really we're only going to work with pico through mega. Okay, the majority of the course is actually from micro to mega, but once we start talking about capacitors, those are, you know, we usually use those in the nano, pico ranges, okay? You know, giga, 10 to the 9th, tera, 10 to the 12th. So you notice that the exponent here is always a power of 3 times n, right? So 3, 6, 9, 12, 15, 18, 21, etc. And the same thing goes for numbers that are smaller than 1, okay? Smaller than 1 but greater than 0. You could also have a negative number that does this, but I'm talking about the number itself is between 1 and 0, or negative 1 and 0 for that matter. So now instead of having a bunch of zeros out in front of our number that we have to count, we do the same thing. Okay, we've got one for negative 3, negative 6, negative 9, negative 12. Okay, so we utilize those powers of 3 to quickly identify what a value is. All right. So, you know, we can work on, you know, converting between the different prefixes. Okay, we're going to do a little bit of that work. And here is what I call a mnemonic device. You may know what a mnemonic device is. You may have learned the order of the planets with a mnemonic device. So I'm going to put that in the comments real quick here. So what mnemonic device do you use to remember the order of the planets from the sun. Okay, my guess is that somebody can rattle that off the top of their head because they had some professor or teacher that, that forced them to do it. How about this one? So what mnemonic device do you use for remembering order of operations? Okay, I always get a couple of different answers on that as well. So what mnemonic device do you use to remember the order of the planets from the sun out? Some of you may not know one, but some of you probably have seen it. Or, yeah, so my very blah, blah, blah. Yeah, I don't even remember it all, Austin. But yes, it's my very easy something or other. Yes. And then PEMDAS, the other way I see it written is PEDMAS. Because really you could do the division or the multiplication either way, right? And so for that matter, PEDSM, PEDSM, or PEDSMA is what it is. PEDSMA. No, I did it wrong again. Achievably. I give up. So let's get rid of that one. And it's PEMDSA. There we go. Right? Because multiplication, division, you can switch around, and the subtraction and addition you can switch around. Please excuse my dear Aunt Sally. What is that one? That is, oh yeah, there you go, PEMDAS. Here's the actual way to do it, and there's this. There are two Facebook sites that always have like these memes and these little. One of them's called Electrical Engineering World. The other one's called I forget what it's called, but let's see here. So please excuse, yeah. Eager, easy would sound. By very eager, the mother just served us 9 pizzas. There you go, right? And so you have these little things that help you remember, something like this. And so this is the mnemonic device that I use for engineering notation, right? If you need that kind of help. So wherever you're at currently, so let's say I'm at, how about 723, 145 volts. That's a lot of volts, okay? So I'm right here in this space. So this is G, capital M, K, nothing, M, mu, N, P, okay? So all I did was take these prefixes right here and then put them in order. So if I'm at this middle place right here, so this is no prefixes right here. That's where I'm at right now with volts. If I want to know how many kilovolts that is, since I'm moving from this space 1 to the left, then what I do is I move the decimal place 3 places to the left. So 723.145 kilovolts is the same thing as 723,145 volts. Okay? If I want to know how many millivolts that is, if I'm right here from 723,000 volts, and I move to the right, well, then I move the decimal place 3 places to the right. So this would actually be, great big number, 723,145,000 millivolts. Okay? So wherever I'm at, if I'm at mega and I want to see how many kilo that is, and if I move to the right, all I do is move the decimal place 3 places to the right. Okay? So how about, let me do this. If you want to, go ahead and try to figure this one out on your own. I'm going to put 0.0000457 amps. Okay? So I want to know how many milliamps that is. Okay? Well, I'm at amps right now. I'm right here, okay? And I want to go to milliamps. So I'm going to be moving to the right. So I move the decimal 3 places to the right. So 1, 2, 3. Now I've got 2 leading zeros. So 0.00457 milliamps. Okay. What about microamps? How many microamps is this? Well, if I'm at milli right now, which is right here, and I want to go to micro, which is mu, then I go 3 places to the right again. 1, 2, 3. So now I'm at 4.57 microamps. Okay. Now, these 3 quantities are all identical. They represent the same amount of current. However, this is the best way to report it. Okay? So one of the things that was on the previous slide that I did not point out is in engineering notation, the number has to be between 1 and 1,000, including 1, but not including 1,000. So over here, this does not qualify as engineering notation because this number out in front, okay, if you want to think about this in 2 parts, you've got the number and then you've also got the unit that tells you what it is. So this is not engineering notation. This is just decimal notation because I don't have any powers, I don't have any prefixes, I don't have times 10 to the anything. It's just here's the decimal notation of this. Okay? This is still not engineering notation. Even though I'm using an engineering notation prefix, a metric prefix on here, the number itself is not between 0 or between 1 and 1,000. So this is really just a number that's using a metric prefix. It is not engineering notation. However, this one, 4.57, the number is between 1 and 1,000. And so I can see that this is 4.57 millionths of an amp. Okay, I don't have to count the number of zeros out in front. I don't have to do any mental gymnastics. I can just see, oh, okay, that's a really, really small current, right? That's 4.57 micro. And as we go along the semester here, if you haven't worked with these prefixes before, you'll get used to them and you'll start thinking about, at least this is the way I think about it, right? I think about micro down here on a smaller level, and then I think milli is just a little bit higher than that, and then I think that, you know, regular units, whether it's volts or amps or ohms, is the next level. So I always think about these in terms of, you know, like what level is the measurement on, okay? So I could take this a step further and say, okay, how many nanoamps are there? That's the N. This is -9, okay? Well, I'm at 4.57 micro, so here's where I'm at right now. Well, I essentially multiply this times 1,000. I move the decimal 3 places to the right, so that's going to be 4,570 nanoamps. Again, all 4 values here are identical quantities. However, this, again, is not in engineering notation because the leading number here is not between 1 and 1,000. Okay? So let's do a few more of these. Okay? Let's say I have 22,000 ohms. Okay? Again, if there's no prefix out in front here, then you're essentially in what we call decimal notation. And that is, you know, 22,000 ohms, or, you know, like if you measure the voltage on your battery, 9.65 volts. Okay? That's decimal notation. So how would I get this into engineering notation? Well, right now, I'm here with no metric prefix. And so if I move it to the left, that gets me closer to a number that's between 1 and 1,000, right? If I move to the right, it's only going to make this number bigger, and I don't want to do that. So if I'm at 22,000 ohms, and I move 1 to the left, 1 prefix to the left, and I move the decimal, 1, 2, 3, I end up with 22 kiloohms. Okay? Now this is a number between 1 and 1,000. So this would be the way I would report this as engineering notation. Now, if you want to take this a little bit further and be kind of scientific about it, I always like for you to give me 3 significant digits, okay? All right, now, let's keep going. How many mega ohms is that? All right, well, I'm at kilo ohms right now, and so I want to take this and move it 3 to the left, and I end up with 0.022 mega ohms. Okay? So there we go. So all 3 of these quantities represent the same amount of resistance, but when you report to me, you're going to report the engineering notation version. Okay? Any questions on that? Okay, so 2 things I want to point out that are kind of from my my metrology days are accuracy and precision. Okay, because a lot of times people will use those terms interchangeably. Accuracy is how close you are to the actual expected value that you know, if I say that this calibrator is outputting 2.5 volts, how close to that is it actually outputting 2.5 volts? In other words, how accurate is it? Okay? Precision indicates how many digits out that you can actually read. Okay? So you could have something that's very inaccurate but very precise. In other words, it has what I would have in my uncertainty budgets was called resolution. Okay? So like your DMMs are 3.5 digit multimeters. That means that you have 3.5 digits of resolution. Okay? So in other words, you could have a 1.246 kilo ohm measurement. Okay? So here's the 3.5. You have the 3 digits that can be 0 through 9, and then the half comes from this one out in front. So your meter actually has 4 places for digits, okay? But this very first one out here can only be a 0 or a 1. Okay, that's where that half comes in. We had a multimeter, the $25,000 FLUB that I told you about, that would measure out 8 places. And so it was an 8.5 digit. So I could make this a, see, 1, 2, 3, 4, 5, 6, 7, 8.5. So we had, and our accuracy was actually out here in these numbers, okay, the accuracy for the device itself. So it's a very, very accurate, very precise measurement tool, okay? Now, I could have something that's, you know, plus or minus 2% that reads this many digits, but sometimes it's not that important to include that much precision if you're not very accurate, okay? That's why for all of the calculations that you do for me, I just want 3 digits of precision or 3 significant figures, okay? I don't need to know what happens down here that your calculator spits out, right? All of this stuff is, you know, there are errors that will account for some of this stuff. So just because your calculator gives you this on your screen, I don't need to see the extra digits, okay? So 3 significant digits works out great. Okay? All right. Another pictorial version of this. So it says, a flow of electrons in the same direction creates an electric current. So in this, I want to be very clear about these 2 terms I'm about to use. Okay? You see here that this is called, the current is moving in what's called electron flow. Okay? So electron flow states that all of the electrons in the negative terminal of the battery flow out through the circuit back to the positive terminal. Okay? That's the reality of what actually happens in a circuit. All right? Now, we do not use that current convention, and I'll tell you why here shortly. We actually go in the other direction. We do all of our calculations assuming that current goes from positive to negative. And you might say, well, that's completely 100% backwards, and I agree with you, but here's the problem. We use conventional current because of one of our forefathers here in the United States, Ben Franklin. okay? He's the one who actually discovered current. He did not measure or discover electron current. He actually discovered silver ion current, okay? Silver ions are positive. The ions that he was measuring, silver ions that he was measuring were positive. So as they were moving, he noticed that they always moved from the positive to the negative, okay? Well, that convention was established for, I forget how many years, I think it was decades. And so that became the standard, right? We just assume that current flows from positive to negative. However, the gentleman who discovered electron flow, and his last name starts with an I, and you'd think after 21 years I'd remember it, but I don't. But anyway, he discovered that, in fact, electrons move from the negative terminal to the positive terminal, all right? But the convention was already set. So there are certain textbooks. One of them we used to use, and his last name was Mead. He actually had two versions of his textbook. He had one version where all of the chapters were using conventional current, and that's the book that we would use, right? He also had a version of the textbook where everything was backwards compared to the other textbook, right? Because he assumed that the current always flowed from negative to positive. And so I always had an issue with some of the students would invariably buy the electron version of the book, the electron current flow of the book, and they would be confused all semester because, and sometimes I wouldn't find out that they had that version until, halfway through the semester. And I'm asking them, hey, what's going on? Why, is this not something you're interested in? What is confusing you? And and the girl told me, I see what you're doing on the board, but then I go look in my book, and it's telling me to do everything exactly the opposite. And I looked, and she had the electron flow version of the book. So now we don't have that issue anymore. And really, the only place I know of that still uses electron flow is the military, because they've got some equipment that's been around since the 50s and 60s, and all of the reference manuals are only written with electron current flow. And so that's the only place I know of that still utilizes electron flow. So I'm going to ask you if you know the difference between the two of these. I'm going to ask probably on the quiz, and I guarantee you it'll be on the exam, that you need to know the difference between the two current conventions. Okay, so again, conventional current, positive to negative. Electron flow, negative to positive. Okay. I'm not going to walk through the voltmeter connections right now. I'm going to draw this on the board so you can see the difference, okay? Because I'm going to talk about current measurements as well. So some of you may notice some of these conductors on here. And letter A, you might find under the hood of your vehicle, because this is a great one for battery terminals for your vehicle, right? So very, very thick. So I have a question here from let's see. So if this is a mistake by Ben Franklin, why are we using it? Well, that's a great question. Because the convention had already been set, right? And so if you've started to publish other books that reference that material, and it just becomes common knowledge in the engineering and science world that that's how current operates, that's how people started doing the calculations, right? So that's the only reason why, right? And like I was just saying, the only people who still use electron flow are the military. So yeah, that's just, it's kind of one of those oddball things, right? So, you don't have to spend too much time dwelling on that, but yeah, it's pretty much, they made the mistake, it became the way it is, so to speak, and then it was never changed, right? So anyway, here you see that this is a much thicker gauge wire, and you would expect that because there's some systems in your car that draw quite a bit of current, okay? So you don't want to have a tiny little 32 gauge wire that's trying to carry all of those electrons. It's going to burn that up. So you want something thicker that has the ability to carry that many electrons and deliver that much current. Okay? The next one you might recognize as coax cable, right? So this is what your Ethernet travels on. There's some shielding around the wire, and then there's an outer insulator. I'm going to skip letter C for just a second and say, does anyone know what letter C was used for? Because I don't see these very often anymore. Okay? So letter D is just a standard, what we call a braided or a stranded wire. In other words, you know, you would buy letter D as a 30 gauge or a 10 gauge or whatever. You still buy it by the gauge wire. However, the wire is not a solid piece like it is with E. That's a solid piece of wire with just an insulator around it. Letter D has a stranded gauge. In other words, there's a bunch of tiny little wires that are all grouped together that comprise that diameter of the wire, and then they wrap it in insulation. So for the wiring that you are going to get in your kits is letter E, right? Because we want to be able to push down into our breadboards and have it stay put. And if you have braided wire like letter D, you know, you have to twist it to a fine point, and then you kind of have to twist it as it pushes into the breadboard, and sometimes it doesn't work. Okay? And so Matt has an answer here. He says, ground? No, not ground. If any of you ever had a black and white TV, okay, relays, not to my knowledge. How about, so I remember them from the black and white TV that we had in our downstairs when I grew up, okay? And eventually I got an Atari 7800. Some of you may, you know, we had a discussion on that yesterday in my 112 class. But when I would have to move the Atari from one room to the other room to the black and white TV, these two things were what connected to the antenna that sent the signal then into the inside of the TV. So, you know, this reminds me of that UHF connection on the back of the black and white TVs, all right? And I remember when I would have to use the black and white TV with my Atari, I would have to slip these little things up in there as an adapter, and they fit right in the same spot. So I believe this is like the UHF portion of the old black and white TVs. You had the regular antenna, you know, that's gonna capture the signals, but then you also had a UHF connection as well. And so Matt says, I have those cables to ground my turntables. Okay, so they may, you know, I believe they still manufacture those kind. And you know, at the end of the day, it's just two pieces of wire, right? And they both come to the spade that's at the end of the wire, and then they make a connection. So there's nothing spectacular going on there. But yes, it's very well possible that you have those for some other use. Right? It's really kind of handy because you've got those two spade blades, you know, right next to each other, and you know you don't have to use two separate pieces of wire and have it be kind of messy. So yeah. So hey, I'll tell you what, Matt, if you could, if you think about it, you don't have to do this, but if you could take a picture of that, I'd love to see how it's connected. So. Just take a picture of that and send it to my email if you want to, okay? Because I would love to see that, because I have not seen this in anything other than, like I said, that UHF connection that I used to have to make. So this is going back to what I was talking about earlier with the actual physical dimensions of a conductor, like a piece of copper wire or something. What the material is makes a difference. How long is it? That also makes a difference. And then what's the cross-sectional area of that wire? Okay? Here's another big factor of resistance is temperature. So I think I even said this in the lecture that, you know, if you're trying to make a voltage measurement or a current measurement or whatever, and you are actually holding the leads in your hand, if you're trying to make a very, very accurate measurement, you're going to distort it because your hands, because your body is at 98 degrees, 98.6 degrees, presumably, you're introducing heat into those leads, and that's going to affect the accuracy of the measurement, okay? So, one of the things in metrology that we always did, if we needed to make a really accurate measurement, is we would use alligator clips or something where we could take our hands off and not be introducing any new heat into the measurement, okay? So the temperature of the wire, the temperature of resistance makes a difference as well. Okay. Now, I keep saying, 10 gauge, 20 gauge, and you might be thinking to yourself, okay, I think I understand what that means. What I'm doing is I'm referencing this AWG, excuse me, the American Standard Wire Gauge, okay? And so this actually works in the reverse from what you think it works. So a higher number gauge is actually a thinner diameter piece of wire. So a 10 gauge wire, here's 0 gauge down here, but 10 gauge is, if we follow this thing around, it's about right here. That's a much bigger diameter than a 32 gauge, which is down here somewhere, okay? So higher number wire means it's a thinner diameter gauge wire, right? Now here's another thing. This is about as close as I get to a trick question in here, right? And I felt so bad about it potentially being a trick question that I've started talking about it in this part of the lecture, okay? If I have a 10 gauge stranded wire, which again, stranded wire is comprised of a bunch of small little wires, but if I have stranded wire and it's 10 gauge, and I also have a solid wire that's 10 gauge, and I say to you, which one is thicker, okay? Well, neither one of them is thicker, right? And so I always get answers like, well, it's the solid, or I'm sorry, it's the stranded, because the stranded has little bits of air in between. As much as you compress those wires together to create a new gauge, there's still going to be little gaps in there, right? Even if you can't see it with your naked eye, there's going to be little gaps. But the point is that they're both 10 gauge, and so they are the same diameter. So that's about, like I said, that's as close as I get to a trick question. So 5 gauge stranded, 5 gauge solid are the same diameter. One is not bigger than the other, okay? And so as you get to the smaller gauges, in other words, the larger diameters, they have the ability to handle more current, right? There's more room for the electrons to move around and to attach themselves to different atoms. And so you can move more electrons very easily. If you don't have as much, the wire is going to get very, very hot, and it could eventually get hot enough that it breaks or burns, okay? So here's a listing of all of the gauges. You can see from, well, not all of them, from 10 down to 32. And you can see that, on a 10 gauge wire, it could easily handle 15 amps of current, all right? So in your walls, you probably have 10 gauge wire. Like I have a 20 amp breaker on my equipment that I use in my garage, okay? And I'm comfortable plugging anything in. Almost none of it goes above 15 amps. And I believe everything is wired with 10 gauge, okay? Matt says it has to do with the amount of balls that can be molded from an amount of material. Can you explain that a little bit more, Matt? Okay, so you can see down here when this is amps, right? And so obviously I would prefer that these were in engineering notation, but that's okay. I didn't write the chart. So like 26 gauge wire will hold up to 363 milliamps. Now, 363 milliamps is still a pretty good size current, okay? A lot of the currents that we deal with, like I said, are like 10 milliamps or 5 milliamps. So very, very, very small that, using a 26 gauge wire leaves you plenty of room so that you're not going to burn it up, okay? I'm not going to talk about the measurements again. I'm going to do a separate video on that. But I am going to talk about current measurements. Okay? So what I'm going to do is I'm going to go ahead and go back to my board as soon as I reset that and give myself a picture and make sure that it's okay. Sometimes it just takes a snapshot and I'm up here talking and the video doesn't change. So again, I'm just going to draw a sample circuit just so we have a visual here. Okay, and it doesn't matter what these values are. 100 volts, 100 ohms, 200 ohms, okay? So if I want to make a voltage measurement, okay, and here I've got red and black, so this is my positive lead on my DMM, here's my negative lead. If I want to make a voltage measurement, I just go make a voltage measurement wherever I want. While the circuit is live, I don't have to stop what I'm doing. I turn the circuit on, I make my connection, it's now drawing current, and I can go make whatever voltage measurement I want, okay? When I put my meter in ammeter mode, first thing I have to do is break the circuit, okay? Now this is something I will emphasize over and over and over, all right? And I even go so far this first time here, if I could find what I did with my blue one. Oh, there's some orange ones. So put a sun out here. I like to draw some pretty ridiculous stuff because I want this point to, I think last time I did some stars, and my daughter likes unicorns. This is about as good as I get for something quick. Okay, so the whole point of me being ridiculous here, maybe some squiggly lines, is I want you to remember to break the circuit. Okay, now you have a meter that you're going to buy, or that you've already bought that's coming, that has a resettable fuse in it. So again, I talked, it's kind of like the thermal fuse in a paper shredder, where if you feed too many sheets of paper over and over, it'll break that thermal connection. Once it cools down, it resets itself, and then you can reuse it. That's kind of how the fuse works on the DMM, okay? But you don't even want to have that happen, so break the circuit. So in other words, this is, if I just look at the component itself, here's my component, okay? That's my resistor. And again, we're going to talk more about this later. But that's my actual component, okay? Where you see the black here, except for the source, but where you see the black, those are just pieces of wire. So when I say break the circuit, I mean, pull one of the legs of the resistor out of the circuit so that you have this. Okay, so I've just pulled the wire out from this connection. You have to make the ammeter part of the circuit. All right, so there's my red lead, there's my black lead. Okay, so it becomes part of the loop. So again, voltage measurement, I can make that anytime I want. I don't have to deal with any of this, okay? But if I want to make an ammeter measurement, I'm going to harp on this over and over and over. You got to break the circuit first and insert it in line, okay? Here's why you do that. If I were to use an ammeter, and do not do this, if I were to use an ammeter like a voltmeter and put it around a component like this, okay, what's going to happen is that current is going to come to this node. It's going to see that there's 100 ohms of resistance here, and then it's going to look at this well, it's not going to do this in real life, right? I'm giving them human characteristics, but it's going to see that there's 100 ohms of resistance here, and if you were to measure the resistance of the terminals while you're in ammeter mode, it's like less than 10 ohms, okay? So you've heard this term before, that electricity always finds the path of least resistance, okay? So it's going to say, well, I could fight my way through here, or I could just sort of skip around it over here. So what you've just done is you've essentially shorted out that 100 ohm, and you've just increased the current, okay? Now, if you do it badly enough, and let's say you accidentally did that, okay, so it's still going to come to this node right here and say, okay, well, you know, I have 100 and 200 ohms here, or I have, you know, less than 10. The whole thing's going to go over here, okay? It's going to completely bypass both of those resistors, and then the only resistance in that circuit is the resistance of the wire, which we know is less than an ohm. That's how you blow a fuse, okay? So you don't want to do that. You want to make sure that you break the circuit, put your ammeter in line so that, you know, as you follow yourself around this loop, right, it's part of the loop. There's no situation where you have this, okay? This right here, the current's going to bypass the resistor altogether and go right through the ammeter, okay? Now that the ammeter has that low resistance on purpose because you don't want to put a high value, you don't want the terminals to be a high resistance value, because when you use it properly, that's essentially like putting a big resistor in here, okay? And that's going to add resistance to the total resistance here in this circuit. So, again, the big takeaway here, please break the circuit, okay? And obviously, this part of the lecture is born out of our lab technicians having to fix these fuses over and over and over, and students blowing up meters in the lab, but this also goes for the meter that you have at your home, right? You don't want to have to replace it or blow it up or even damage it, okay? All right. Okay, so he says, I think it was a steel ball, but if you could make 10 balls, it's 10 gauge, 20 balls. Okay, okay. Oh, I got you, That makes sense. And then it has to do with the surface area that the balls take up. Okay, all right, very interesting. All right, so let's look at the next slide here, and we've got, again, this is a visual representation of what I was just saying, okay? So here we have a light bulb, here we have a power supply, and you can see that this is connected in what we called series. If it's part of this one loop, then all of this stuff is in series with each other. The other term that we use in circuit analysis is called parallel, and we will get to that in chapter 7, or I'm sorry, in chapter 6, okay? So everything we do up to chapter 6 is going to be in series. So, you know, just to kind of introduce this early, if you have one loop here, this is a series circuit. So you have all of your components connected together in that one loop, and that goes for this ammeter here, okay? The other thing I like about this little picture down here is this one still has things in electron flow. You can see the electrons are moving in the opposite direction of what we teach. But that, again, that's the reality of what happens. That is not how we calculate things, though. So again, so you're not really going to annoy me this time because I'm not in class with you, but it says never connect the ammeter across any circuit element. Always insert the ammeter in a break you broke in the circuit. If you connect the ammeter across the power supply, you will blow the ammeter fuse or damage your DMM, which is bad news. We don't want to do that, okay? So break the circuit. Okay, we're not going to worry about that one. Okay, so I like this picture. This is from the Mead book, well, actually I think it's from a different book that Mead referenced, but anyway, so here we have another pictorial representation of a resistor in series with this battery. Okay, we've got some alligator clips here just to show that we have the ability to break the connection. So here's the circuit that goes along with that. Just one voltage source and one resistor. We haven't talked about schematics yet, but you can see that here's the pictorial representation of this schematic. Okay, so we break the circuit. In other words, we make a spot for this to fit. We insert the ammeter in its place, and you can see here, and I'll point this out throughout the semester as well, is the circuit current you want going through your meter positive to negative. So the positive side should be closest to the battery here, and the negative side of your DMM should be closest to the negative terminal of the battery. Okay? Does everybody see that? If you were to plug them in backwards, in other words, if you had the positive terminal of the battery going into the negative of the DMM, and then the positive going to the negative here, all that would happen is this would read negative 4.1. So it's not like you're going to damage it if you accidentally get the leads backwards. It'll just measure negative. However, there are labs where I want you to switch the polarity of the battery, and it's very important that you have them connected the proper way. Okay? So again, we have our closed circuit here. We break the circuit, we insert the ammeter, and now we can go ahead and make a proper current measurement. Okay? Are there any questions? Okay. If there are no questions, I'm going to go ahead and do a few more of these engineering notation. So if you have your calculator, go ahead and get it out now, okay? If you don't have a calculator, just watch, and then when you do have a calculator, if you still have to buy one or whatever, you can go ahead and re-watch this portion at a later time, okay? Now, I do have, and I guess since I'm inside right now, I guess I'll go grab it real quick because I think it's close by. Okay, I'm going to switch back over to the camera mode, and I'm going to show you my calculator. All right, I have the... Oh, is it registering me? Now is it registering me? Nope, it's not registering me. Let's see if we can... There we go. Now we're live. Okay, so here is my TI-89, okay? And if you do have the 80 series, you should have a mode button that you can press. And I don't know how well this is translating on here. I'm going to do another video on this later, but it is the, let's see, for me, it's the fifth one down. And it says exponential format, okay? I put mine in engineering mode all the time, okay? If you have a TI-30 series, then you have, I believe you have a mode as well. Some of the series have a mode and some of them do not. You may also have on your calculator, you may have some button that's like SCI/ENG. That just says that you can put it into scientific notation or engineering notation. If you have the ability to go into your settings on your calculator, whatever kind of calculator you have, and keep it in engineering notation all the time, okay? That way you don't even have to use that mnemonic device when you do a calculation, okay? So the sooner that you can learn how your calculator works, the better. And like I said, if you have trouble with this, you can go ahead and email me and say, here's what kind I have, and then we can work from there, okay? But you should have either a mode that lets you put it in engineering notation all the time. Some of you have a key that probably looks like that. And so what you'll have to do is do your calculation, hit enter or equals, and then whatever number it spits out, you just hit the engineering notation key afterwards, and it will automatically put it into the proper notation, okay? So, I want to do, here's a preview of what you might see on a quiz or an exam, okay? Where I have 3 separate columns, and this one is decimal, this one is scientific, this one is engineering notation, okay? And so I give you one of the 3, and then you have to put it in the other 2. So let's do a few of those, okay? Let's just start with a decimal number of, what do we say here? How about 0.00352 meters? Okay, so it doesn't really matter what the unit is. 352 meters, okay? What's the scientific notation of this? Well, I've got the number 0.00352 meters. Okay, so if I look at my GMK underscore M mu and P, that's my mnemonic device for engineering notation. But what about scientific? Remember that scientific notation, the number has to be between 1 and 10, including 1, but not including 10, okay? So really, I just need to get this into something that's between 1 and 10. So I move it 1, 2, 3. That gets me there, right? So the scientific notation of this is 3.52 times 10 to the -4th meters. And so that's what you would put in this column right here, okay? Here's the scientific notation. If I wanted to put it in engineering notation, I don't even really have to use this mnemonic device. The way I do it is I say 0.00352, and all I do is hit enter. And because I have my calculator set to report in engineering notation, basically that's a quick way to convert it. And it tells me 3.52 times, wait a minute, 1, 2, 3, this should be 3 here, sorry. 3.52 times 10 to the -3, okay? So you notice here, this one was already in engineering notation, just by chance of the number that I used here, okay? So the engineering notation would be times 10 to the -3 is milli. So this would be 3.52 millimeters, okay? It's also the same thing as 3.52 times 10 to the -3 meters, which is also the same thing as 0.00352 meters. All 3 of those quantities are identical. It's just a difference in how we report them. But this will be ultimately, down the line, this is where I want you to report your answers, okay? So let's do another one. How about I give you the scientific notation this time, and I say, I don't want to use 3 again. Let's use 1.945 times 10 to the 8th volts. Okay? So I want you to give me the other 2. I want you to put this in decimal, and I also want you to put this in engineering notation. Okay? The engineering notation I can go ahead and do quickly. All I do is say 1.945 times 10 to the 8th equals, and it spits out 194.5 mega ohms, because it spit out 194.5 times 10 to the 6th. Okay? You can manipulate this if you're at 1.945 times 10 to the 8th volts, okay? And you say, okay, if I move this one place to the right, all right, I'm actually making this number bigger, which this number should then reduce, right? And so 19.45 times 10 to the 7th, okay? And then do it one more time, 194.5 times 10 to the 6th. So if you move the decimal to the right 1, you have to subtract from the exponent. If you move the decimal to the left, you have to add 1 to the exponent, okay? Or you can just forget all that and just punch it into your calculator and let it do the work, which is what I prefer to do, okay? So now we need to figure out what this is in decimal. Well, I always like going from the engineering notation because this tells me exactly what it is, how many zeros I need. If I have capital M, that's six zeros, right? Because that's millions. K is 3 zeros, so all I do is 194,500,000 volts. Okay, so that's the decimal notation of 1.945 times 10 to the 8th volts. Right? It's also the decimal notation of 194.5 mega. Well, I used ohms there. That's not ohms. That's volts. Okay? So this number and this number, or I shouldn't say number, this quantity and this quantity and this quantity are all identical. Okay? Now let's work from the other way. Let's say I give you 252 micrometers or micrometers. 252 micrometers. Okay? Well, I know that this is 10 to the negative 6, right? So I move the decimal 6 places to the left. 1, 2, 3, 4, 5, 6. So the decimal representation of this is 0.000252 meters. Okay? If I want to find out what the scientific notation is, okay? Well, if I go from here and get myself to a number that's between 1 and 10, 1, 2, 3, 4. So 2.52 times 10 to the negative 4th meters. Okay? Jump over here and see if we have any questions on this. Oh, I got the picture back, and then I didn't switch back over. I apologize. Okay, so just a quick recap of all that I just did. I apologize for that. So we started off with this one, this 0.00352 meters. Okay, and here's the 3 columns that I would set this up with. And so the first one, you know, I can just redo this real quick. So the first one is this 0.00352. Scientific notation 1, 2, 3. So 3.52 times 10 to the 3, negative 3 meters. Okay, because I'm moving it to the right. All right? So to find this in engineering notation, it's already in engineering notation because this exponent is a power of 3 times n. So negative 3, negative 6, negative 9. So it's already in this form where I can say millimeters. Okay? And then the next one I did was give you this 1.945 times 10 to the 8th volts. And then I punched that into my calculator. It spit out 194.5 millivolts. And then over here, that was 194,500,000 volts for the decimal version. Okay? The last one that I just did, 252 micrometers, is 0.000252 meters, right? So I know that this is 10 to the negative 6th, so 1, 2, 3, 4, 5, 6. And that's how we get that decimal number. And then to figure out the scientific notation, I have to get this number to where the front number here is between 1 and 10. So I can take this decimal value here and go 1, 2, 3, 4, and get to 2.52 times 10 to the negative 4th meters. Okay? So now that you see that, okay, great. All right. So any questions on this? So if you want some practice, just do what I did. Just come up with a number, and then, you know, put it in decimal, and then see if you can convert it to scientific and engineering notation. And then also see if you can write down a scientific a number with a unit, doesn't matter what the unit is, and then try to put it in engineering notation and decimal, and then also take some engineering notation and try to go the other way as well, okay? Because you're going to see some of these conversion problems, okay? Any other questions? All right, well, if there are no other questions, then you are free to leave. Right? And you know, like I said, if you are doing the homework and you come across one that you have a question on, just send me an email and I can help you work through it. So again, I'm not going to give you the answer on the homework, but especially if you take a picture of what you've already done on the problem, I can tell you where you went wrong. Okay? All right. Hey, no problem, Austin. And like I said, if nobody else has any questions, then you are all free to leave. And I appreciate you guys showing up today.